Hi everyone, welcome to our presentation on our project, which is Astrophotography Made Easy. A little bit on the motivation behind our project. Um, if you've ever done astrophotography, you know that it requires a lot of specialized skills. You need to know a lot about both photography and about astronomy. It's also very expensive and it takes a lot of time to learn and to get the awesome pictures that you want and to process those images and everything. And last, you're tired and cold. You have to stay up all night taking these pictures, making sure it's tracking correctly, and it's often very cold outside. And so, for lazy people like us, we wanted something that would do all of this for us. So now you don't have to do that. Now you can just stick everything in a queue, all the stars you want in a queue on the app, go to sleep in your nice warm bed or sleeping bag, and wake up the next morning with a bunch of awesome pictures.
Yeah, so this is an overview of our entire system. The basic idea of this is that you have a front-facing app on a phone that allows a user to select a visible star in the sky. And then we'll have a telescope and a camera system that will slew to that location, take pictures as instructed, processes images, stack them, and return them to the user in the app. So the flow can be seen from the Stargazer app, which you can see on the top left. Those requests go down into the code that we're going to call the left side of the interface. It goes through this thing that we're going to call the Alpaca interface and to this code and hardware on the right side that we'll call the right side of the interface. And so really what our system boils down to is we have this code on the left, the code on the right, and the Alpaca interface. And ASCOM Alpaca, it's a standard used in many professional astronomy instruments. It provides an interface. You still have to implement all of the software on the left and the right side. So it requires you to implement functionalities like starting exposures, slewing telescopes, getting image data, etc. It's not super nice to work with. There's lots of extra overhead that you have to use. But the advantage of it is that if your setup is Alpaca compliant, you can take your left side and switch it out with someone else's left side, and your mount and everything will still work the same way, or the same. You could take someone else's mount, and our app would still be able to control it the exact same way. And so deciding to make our system Alpaca compliant influenced lots of large design choices that we had for this project, but the benefits for it are very good. So now I'm just going to talk a little bit about some of the setup and the left side of the interface that we saw earlier. And so all of our setup and running of the code is facilitated by Docker Compose. Split of lots of components of the project into their own Docker containers. So we're using a Swarm eval kit with a Swarm M138 modem. We use this to get data such as the Greenwich mean time and GPS information, and we interface with it over UART. And so the startup steps kind of look like this. We start Redis, which is a database and a communication system that we're using in a few places in the project. We start the image processor and the camera controller. We wait for GPS data from the Swarm, and then we send that information to a Raspberry Pi Pico. More on that later, and we wait for the response. We wait to get the Greenwich mean time. And then we start the left side of the interface, which is the Stargazer Server Alpaca client. And then we start the right side, which is the Alpaca server. And so each piece of these creates individual log files as well as a combined master log so that we can see what's happening in real time. And using Docker Compose and these entries with these Docker containers is really awesome because it makes it as easy as typing Docker Compose up to bring up the entire project. So this is just a little bit more on the left side of the interface. This is the client of the interface, so it makes requests to the telescope and the camera. The Stargazer server receives connection requests from the Stargazer app, which was on the phone, a little bit more on that soon, and it will hand those off to a new thread. It allows control of things like the star queue, and it lets users search for stars and add and remove requests. It manages connections, available stars, favorite list, and displaying completed and processed images. And it allows multiple concurrent users. And then we have the Alpaca client. It talks directly to the Alpaca interface. So this is where we're actually telling the camera and the telescope to do things. It receives stars to image from the Stargazer server, and then it gets that image data back and hands it off to the image processor. And then the image processor sends those completed images to the actual image processor, more on that later, and waits for the results. And then it passes those stacked and processed images back to the Stargazer server to view in the app. And then this is the Stargazer app. It was written with the Flutter framework. It's compatible with Android, iOS, and even a web app. We implemented what we call the autonomous mode. It lets users search for stars that are available in their sky and select an image quality. This is where kind of all the magic happens. So it'll command the setup to slew and take pictures of the requested star, get images back, process and stack the images, and then return the final image so that you can see it within the app. And so this is where we can take a lot of the hard parts of astrophotography away and make it a lot simpler in the user's perspective.
Next, let's talk about the right side of the Alpaca interface. The right side of the interface is the Alpaca server and the software controlling the hardware. For our server, we use Django. Django is a web framework built for Python web servers. And for our microcontroller that interfaces with the hardware, we used a Raspberry Pi Pico. And the hardware is interfacing with that we're interfacing with includes two TMC2209 motor drivers, the kind you'll see on a lot of 3D printers, a 9-axis IMU, and a little OLED screen, and a Sony a7 III, which we'll talk more about later. Our Alpaca server is using Django, and in retrospect, this may have been a bit much for our simple use case, especially running on a Pi. It might have been better to use something like Flask, but we're already familiar with Django. In our server, we include support for all of the Alpaca endpoints. Again, I want to stress that Alpaca is only an interface that dictates what information is sent and received from each endpoint. The implementation was up to us. The interesting parts of our Django server are what we call our UART queue, which takes all of the different threads running on the Django server for each individual request and makes them synchronous before we send them to the Pico, since the Pico can't handle the same sort of concurrency that a Pi can. When we get a response back from the Pico, we split it back into the proper thread using unique IDs. We also built a timeout decorator for communications with the camera and with the Pico so that we won't get hung up on a request if something in another part of the app breaks. We try to focus a lot on making individual parts of the project robust against other parts of the system breaking, and keeping everything separate like this allowed us to more easily recover from errors. In most cases, our entire system is very capable of recovering from errors, and restarting necessary parts of the system to keep everything running. For example, let's say we're trying to stack too many images at once on the Pi, and it's not capable of doing so because it doesn't have enough memory, so it crashes. Our system will recover from this, all the pieces will keep working, and we'll restart the image processor. Next, I want to talk about controlling the hardware, but it will be helpful to understand equatorial coordinates first. Equatorial coordinates are analogous to spherical coordinates, except that they are independent of the observer's location on the Earth and the time of observation. Right ascension and declination are absolute, and your position and time just create an offset right ascension and declination that you have to factor for in your calculations when finding a star. Another way of thinking of this is that right ascension and declination are like longitude and latitude on the Earth, except instead of giving a location on the Earth, they're giving a location on a giant imaginary sphere in space around the Earth. Now let's talk about the hardware. We have two motors, one controlling right ascension and the other declination. This is nice because it allows us to simplify some logic and get really smooth tracking of the stars. Miguel will talk more about how we accomplish this in our setup with a 3D printed equatorial mount in a little bit. We're controlling the two stepper motors with the Pico. The Pico is using UART to communicate with our TMC2209 motor drivers, and the TMC2209s have a really nice interface, so we don't have to send pulses to the motor if we don't want to. We can just write a speed to register, and the chip does the rest for us. We did actually end up sending pulses as well, though, for finer motor control. The Pico is also connected to a 9-axis IMU that gives us our current orientation. We can get our roll, pitch, and yaw and convert those to equatorial coordinates when we are saluting the stars or tracking. Finally, we interface with a little OLED screen that can display information to the user during polar alignment and other helpful information throughout the operation of the mount that doesn't make sense to display in the app.
All right, so as for power and the physical design of this system, we really wanted to make sure that we had enough power to last us all night. We didn't really think it was a good idea to have a system that you'd want to power all night while you're sleeping and not be able to have it take pictures while you're, cozy in bed. So in order for power consumption to not be an issue, we needed to take into account all of the things that would be consuming power. So we have a Pico that's drawing roughly 100 milliamps on average. The Raspberry Pi 4B is actually the beefiest thing here. It's drawing roughly 600 milliamps on average. And each of the motors can draw up to 1.4 amps during peak usage. But I noticed that it was roughly only about 200 milliamps on average while we're actually using them. So this was in combination because of not really necessarily needing that much torque. The camera doesn't really weigh that much, and it doesn't have to move a lot of weight very quickly. It just needs to track. So in the next slide, we'll actually see a little bit more about the batteries. And the batteries themselves are a really good choice here. The INR Samsung 18650 30Q battery is ideal for this kind of scenario. It packs a lot of power. It's got very high power density. And specifically what it can do is it can supply that power in a continuous manner. So you can have a 15 amp continuous draw from a single one of these cells. Um, it's relatively light, and you get all the power necessary to last you all night. So we also needed about 70% of the voltage to be retained to keep the battery from degrading over time. As you can see here in this graph, it actually shows that some of the cells that we had here were not very good. They were actually a little bit worse in the performance range than the cells that we would have expected to get. But that's why we over-engineered the battery a little bit, and we made sure that we had enough power. So an 8 series 4 parallel battery gives 32 cells, and 32 cells at a nominal 4.2 voltage gets us to roughly 34 volts. So in the ideal scenario, that would have been about 12 amp hours, but it didn't actually end up coming out to that. It's roughly about 10. But in order for it to last all night, that gives us about 9 volts of usage before we actually get to that 70% range. So that's roughly about a 1 volt drop per hour. So another thing that we needed was the PCBs in order for this system to be, working seamlessly. Unfortunately, we didn't get the Pico board manufactured in time, but we were able to make do with a proto board and putting all the pieces together ourselves. So as you can see here on the bottom left, you can see the Pico and the screen, as well as the touch capacitive button. It would have been nice to have this whole system as one full unit, but ultimately it didn't need to be. We can have jumper cables connecting everything, as you can see later on in our design. But on the right here, the motor drivers are actually one of the things that ended up having some signal integrity issues that necessitated a 4-layer board. So as you can see there, the boards on the bottom, those 4 are actually the ones that we ended up using in the system. So as for the 3D printing, on the next slide, you can see pretty much all of the stuff that I went through, but this doesn't do it justice really, because each one of these parts necessitated its own level of iteration, its own tweaking, and a lot of things were necessary in order for all of these parts to come together. In the center there, you can see some gears that were made out of resin. Those actually didn't end up working out very well because resin tends to be brittle. So we ended up actually using something called TPU, and TPU has a little bit of give. So that actually came in handy when it came to printing the gears, but not just the gears. Also on the right there, you can see these 3D printed bearing assembly pieces. So a bearing is a very, very important part of making this thing work, but it was very difficult to come up with something that would work out and not be brittle. So using this TPU actually ended up being just fine. On the bottom here, you can see the whole system together. And this mount, in order for it to be able to track stars, we wanted to make sure that it would be aligned to the North Pole. And then also, we wanted to have it so that it was only a single degree of freedom while we were moving. So in order for that to work out, we would align them out. And from there, we just decide what the declination angle is. And then we only have to worry about the 15 degree per hour drift. So using the TMC 2209 motor drivers, which have a 256-step interpolator in it, that allowed us to get to that 15 degree per hour drift. And on this next little image here, you can see that all of this, in order for it to not get tangled up and messed up, it needed to go through a slip ring, which actually caused us some signal integrity issues with USB. But it ended up not being a problem since we solved that, but it's still something to consider.
So now let's talk about camera control and image processing. This was the portion of the code that I spent the most time on. We can roughly divide the camera control and image processing into 2 categories. We have the front end that's written in high-level language, in this case, Golang. It communicates with Redis and the Alpaca server, as well as relaying all the messages to the backend C, which takes control of the actual heavy lifting. That's the camera commanding and the image processing. C is a very great language for this. It's very fast and it's a workhorse, but it doesn't provide a lot of the useful things that a high language like Go does for interfacing with Python and Redis. So roughly the process looks something like this. We have the Go that listens for commands relayed on a Redis channel. Depending on the command received, it executes the appropriate command, or rather it forwards the appropriate command to C. C does the heavy lifting of actually taking the image and as well as processing the image depending on the request that was relayed. And then finally, the response is sent back to the Go caller that relays the response back to the Alpaca server. At that point, the image processing and image capturing is done, and the Go front end will continue to listen for new requests. Requests listen on separate threads, so it can actually process multiple requests at once. The image capturing is handled using gPhoto 2. This is an open source library used for commanding different digital cameras. Very robust library written completely in C. And we use the command line interface that it provides in order to interface with the digital camera. The image processing portion is handled by OpenCV. OpenCV is an open source library that OpenCV is an open source library that handles image processing and a whole lot more. In this case, we're using the image stacking capabilities and the image colorization capabilities of OpenCV in order to produce an image that has a higher signal to noise ratio than would otherwise be possible. It says OpenCV is written completely in C++, and our Go frontend can only interface natively with C programs. We had to write a C wrapper to interface with, to really go between OpenCV and Go.
Okay, so we're going to do a final overview of our project functioning. So right now all of the software is up, and right now it's waiting for data from the swarm. The swarm doesn't work inside, so we're just going to use my computer to be the swarm. So what it's doing right now is it's going to send it GPS coordinates, your time, and your elevation. You need a lot of that info to know where you are in the world because it changes how we want to tilt. So right now what it's doing is it's tilting. It's looking at 90 minus your latitude. This is going to be important when we are equatorially aligning it. So now it's pointed that way. So now we're going to manually go ahead and move it. And we're going to move the camera until it goes back to be level with the Earth. And so this is the second step of equatorial aligning it. So on the screen we have some info that just shows the current, the tilt. And so we're going to get it there, and then we'll hit a button telling it that it's good, and it'll go back. And right now it's slewing to our altitude, or latitude rather. And now it is equatorial aligned, which means it's looking directly at the North Star. This is important for when we're trying to track stars in the sky, because we can just use one motor now to follow stars perfectly because they go around the North Star. So let's see. So I just need to send it some more data. This is what the swarm would be doing if it was functioning in here. And so it got all that data, it knows where it is, and it's ready to track stars. So now we're able to use the app to select stars.
All right, so I'm going to boot up the app, and we'll be doing a concurrent screen recording with the app. And we're going to first connect to the server, and we see two modes. We're going to go into the autonomous mode because the under development mode that allows the mount to follow the camera is not finished yet. So in the autonomous mode, you can add stars. So we have a list of stars that are visible in the sky right now. And what we're doing is we're using something called the Hipparcos catalog, which is a catalog of, I think, 11,000 different celestial objects in the sky. And we're filtering that to only have these stars visible to us in our sky, at our position on the Earth, at our time, at a specific time. So let's go ahead and tell it to go to Akerd. And we see that you can adjust the quality of the image that it takes here in the app. You can, what this does is it changes the number of images that it takes and the exposures of each of those images for when it stacks the images at the end. So we're going to select a potato quality for it to go quickly. We'll add that to our queue. And if we wanted, we could add others to our queue as well. And then we submit the queue, and In a minute, we should see after we refresh, it just took accurate out of the queue. So it's going slew to accurate now and take some pictures.
So the first thing it does is it's going to slew to the correct declination. The declination tells you how far from the North Star it is in a circle, like how big that radius is. So it'll slew there first, and then we just need to figure out where in that circle it's supposed to look. So first you tilt, then you rotate, and then now we know we're looking directly at accurate. It's somewhere up in the sky over there. So now it's going to take 2 images. The quality that we chose took 2 images at 0.1 seconds each. So it's right now just taking them. It takes time to issue the command, actually take the image, and then decode that image and relay that information back. So it's taking number 2 right now. And then what it'll do is it'll get those images and it'll send them off to an image processor. And then right after it begins that image processing, we'll actually be able to start another movement. So we can have lots of things ready for it to move to before we can process the rest of them. So what it's doing now is it's going to re-find itself to home. That's important because right ascension tells you where it is in the circle. That depends on your time and the angle on the Earth. And so if you're starting at the bottom, you can count how far you should go within that circle to find the star. So there we go, just got the second one. It's going to start taking images, so it'll take number 1. And it looks like the other one just finished processing. So that should get back in the app in a minute.
So now we can start refreshing in the app, and we see that accurate showed up back in the app. So if we tap on it, then it'll take a minute because it has to stream all the way back from the Raspberry Pi. In a second, we should be able to see that here in the app. And we can see, obviously, it's not a picture of accurate because we're indoors. But we got a nice picture of the roof.
Or raft
ceiling.
ceiling. The ceiling, yeah.
And the image processor is just choosing a random color to colorize it each time. And so this time it looks like it colorized it green.
The image processor has a front end of a Go interface that listens for requests from the Python server, and then once it receives those requests, it passes the images that were captured from the camera over to C, where we use OpenCV to stack and process the images. The reason why we are applying a false color profile is because this camera is taking pictures in the full spectrum, and that means that the images come out looking a little bit strange or discolored, and what we do is we'll convert those to black and white and then apply a false color profile over the top of them. And as was said, the choice is a random choice in 21 selections that we have.
We're going to look at a few more features of the app. So we're going to connect and go into the autonomous mode. And we're just going to look at some of the things that the queue can do. So let's search for some stars. And we're going to favorite them up here at the top. We're just going to go through and favorite a few stars. So now that we've favorited a few stars, what we can do is we can actually go to our favorites list. And we can see the list of our favorite stars. Let's add all of our favorite stars to the list. Now that all of our favorite stars are in the queue, we can reorder them however we want. And we can also remove them from the queue. So let's remove that one. And now that we've submitted that, we can go back in again, drag these around to reorder them. And then we can submit that. And once it's slewed there, once it's slewed to that star, we can that star is no longer in the queue, so we can no longer reorder it. And it's now taken all of the stars. If at any point there is if there's an inconsistency, like if there are multiple users trying to submit requests to it, and or if I'm reordering it while I'm reordering it, one of the stars in the queue, it then begins to slew. Then we just made it so that the last user will win, or that it will ignore the reorder that I just gave it. So in that last case where I was reordering it, and it began a slew on one of the stars that I was currently reordering, it just discarded what I had sent to the server. And that's it.
Dope.